We present Relightable Holoported Characters, a novel method for creating photorealistic, relightable and dynamic, full-body avatars from sparse-view videos. Given sparse RGB views of a subject and respective skeleton tracking, our method enables relightable, photorealistic novel view synthesis of a dynamic subject under any arbitrary environment and novel poses. This allows us to generate effects like the bullet time effect in an arbitrary environment using a lightweight, easy-to-use setup at test time. Our model efficiently computes the rendering equation in a single feed-forward pass, enabling relighting to arbitrary environments with global illumination effects. We also show our method generalizes to one light at a time, lighting conditions despite not having seen these lighting conditions at training time. Please notice the accurate self-shadows and specular effects. Existing state-of-the-art telepresence methods are able to generate photorealistic avatars, but are only able to recreate avatars in captured lighting conditions, which look out of place in different environments. For example, notice that the color tone on the subject does not match the one of the background. On the other hand, existing relightable avatar methods look consistent with the environment, but do not use image conditions, and are unable to generate photorealistic avatars. There also exist works for image-to-image relighting, which in conjunction with existing telepresence methods can enable relightable telepresence, but these are not consistent across time and degrade the photorealism of the avatar. To address these limitations, we present Relightable Holoported Characters, which takes as input sparse observations of the subject and uses a coarse-defined representation, guided by a set of carefully chosen physics-informed features to enable photorealistic, relightable telepresence under arbitrary environments. For training, we present a novel data capture scheme tailored towards dynamic full-body relightable avatars. We use a lightstage system with multi-view cameras with precise temporal alignment. Our data capture scheme consists of relit frames where random environment maps are projected onto the lightstage, directly simulating diverse illumination conditions. These are densely interleaved with uniformly lit tracking frames. Now we present our method. As our input, we have the tracked skeleton motion, sparse view images, the environment map we want to simulate, and the camera viewpoint in which we want to render our avatar. First, we use a character animation model, deep dynamic characters, to get a coarse template mesh alignment using only our skeleton motion. Next, we generate some physics-informed features in the UV space of this tracked template mesh. We pass these features into a network called RelightNet, which outputs per texel, 3D anisotropic Gaussian parameters. This network is also conditioned on the input environment map using cross-attention mechanism. The predicted Gaussians from RelightNet are placed back onto the mesh and splatted into the given camera viewpoint. For our physics-informed features, we take inspiration from the rendering equation. We first model geometry features. For this, we have the position of our subject from UV on projection of the tracked template mesh, as well as the coarse normals and the high-frequency normals which we extract from image observations using a foundational model. Next, we get albedo features from our image observations. These are refined further using albedo.net. Finally, we get the diffuse shading which encodes visibility information and the camera view direction in the form of the camera encoding. Here, we show the coarse-to-fine representations of our pipeline, from the tracked skeleton to the deep dynamic characters mesh, and finally the dense Gaussians in the UV space of the tracked mesh. All these contribute to the final relit dynamic avatar on the right. This coarse-to-fine representation allows us to generate highly accurate renderings. Next, we show some of our physics-informed features. These are used to guide the final rendering. Notice that our diffuse shading feature is able to capture direct self-shadow effects. Also note that our method is able to recover high-frequency wrinkle geometry and shading effects. We now show some qualitative results of our method. We show 3 subjects rendered under novel lighting conditions. Our method produces consistent relighting across dynamic motion. We highlight that this motion was unseen during training. Next, as the subjects remain static and the environment maps rotate, we observe stable lighting adaptation, with correct changes in shading as the light sources move. We now present additional qualitative results from our method, where we rotate the virtual viewpoint. We first show the skeleton tracking, followed by the recovered geometry and the final relit result. This illustrates how our pipeline progressively refines the representations, from coarse to fine. We show our results across a variety of subjects, demonstrating the ability of our method to generalize to diverse clothing styles and subjects. We show variation in 3 dimensions, lighting, viewpoint, and poses, and show our model generates consistent photorealistic renderings across all of them. Our method uses sparse-view inputs to generate photorealistic avatars, which look natural when placed in any given environment. We can enable natural-looking telepresence by relighting multiple avatars to their digital environment, where they look in place and consistent with each other. Next, we compare our approach with existing methods. We find that motion-driven relighting methods benefit significantly when trained with our data capture scheme, achieving better disentanglement of parameters and generalization to novel lighting conditions. However, our own method, using the same data capture setup, achieves the highest performance overall, demonstrating the effectiveness of our approach. We also compare to a non-relightable, sparse image-driven telepresence method, which we augment with an image-to-image relighting method. We note image-to-image relighting approaches struggle to produce consistent results, whereas our method delivers accurate, highly photorealistic relighting that preserves even subtle facial deformations and expressions. We also show our method's ability to generalize to one light at a time lighting conditions. Note that we do not use any one light at a time environments during training. We note our model's ability to capture self-shadows and specular effects, especially in the hair. Next, we ablate some of our design choices. On the right, the diffuse shading from a single light source is visualized. On the left, our rendering combines a fully lit environment map with this single light diffuse shading. Notice how the shadows in our results align perfectly with the reference shadows. This shows that our method can disentangle lighting effects and preserve realistic shadows. Next, we show our results with skeleton tracking obtained from our runtime sparse views. Compared to the tracking obtained from dense views, we observe a minimum decrease in performance. We ablate the number of lighting conditions required for our network to learn the correct relighting and observe increased overfitting as the number of training lighting conditions decreases. We also ablate the effect of the number of views on the performance of our method. While our network gives photorealistic results across different number of views, on decreasing the number of views, we observe hallucination and decrease in preservation of fine details compared to ground truth. We show the ability of our pose-only model to relight an avatar captured in arbitrary diverse lighting conditions. Thanks for your attention.